Uh, Hello, everyone. I am Mominul and my colleague Zinan. We work for Microsoft in a small team called Linux Systems Group. I'll be co-presenting with my colleague about the CVM performance on QEMU, KVM, and Linux root partition for Microsoft Hyper-V using Cloud-Hypervisor as the VMM. So when we talk about Microsoft, everyone is a little bit interested what Microsoft doing in Linux and open source. We are heavily into Linux and open source, and the stack we have been working on recently. I will be presenting in this slide what are this virtualization stack that. So in this diagram, you can see the traditional Microsoft Hyper-V. It works on top of hardware, and we have the root partition as the Windows. As you know, like the type 1 Hyper-V, like JN, hypervisor, you usually have the host partition, and this has been the Windows for a long time for us. And our team, Linux Systems Group, we have been working on an alternative operating system where we brought up Linux as the root partition for Microsoft Hyper-V. So the purpose of this stack is, like, a lot of customers, they will be interested in using Hyper-V, and also they want to get benefit from open source Linux-based operating system. So that's why we want to combine the power of Linux and Microsoft Hyper-V, where we can cater to the need of Linux native customers who need the virtualization stack. And this could be as an alternative of KVM, QEMU, Vert stack. So let's zoom into the Linux root partition we have with the Microsoft Hyper-V. So we have the hardware and the Microsoft Hypervisor, and we have the Linux root partition. In Linux root partition, we have a kernel module. It's a dev MSSB. You can say it's some kind of similar to dev KVM. And this module exposes some of the IOCTLs to, like, manage and create the virtual machines on Microsoft Hypervisor. And this driver, we have some patches already upstreamed in the Linux source tree, and also some of our patches are in pending review. So it would be great if you folks could review and give us feedback. For the virtual machine monitor, we are using Cloud-Hypervisor. You know, like it's a lightweight and Rust-based VMM utilizing the Rust VMM crates. And Cloud-Hypervisor is also a member of Linux Foundations. So Cloud-Hypervisor has KVM support. We, as a Microsoft, we added the support for Microsoft Hypervisor to launch guest. Cloud-Hypervisor supports both Linux and Windows as the child partition. This slide actually compares the stack on the confidential VMs on KVM, QEMU versus Microsoft Hyper-V and Cloud Hypervisor. So you can see on the left side, the firmware is used OVM or UEFI, and in our stack we are using a new file format that made by Microsoft. It's called IGVM, Independent Guest Virtual Machine. So in the confidential VMs, we have the AMD hardware on top of that QEMU KVM, and on the right side we have the difference is like how we launch the VM. In the case of KVM and QEMU, we use the OVMF, and we on the right side for the Microsoft Hyper-V, we use IGVM. So IGVM is a blob file that is generated by a Python script that is already been open sourced, and the script has a Linux loader that can embed Linux kernel, initrd, and that script can generate VMSA page on the fly and put it into a single IGVM file, which will be later used to load the guest with the specified memory contents from the IGVM file. So for the rest of the talks, when I say CVM, I meant to say confidential VMs on SaveSNP with AMD SaveSNP. But we know AMD, the other vendors like Intel TDX and ARM CCA, they also support confidential VMs. Let's try to describe more into the what is IGVM file that we are trying to use. You can say it's a vert stack agnostic way to package the launch information for a guest and into a single file. And this file is, you can say it's some kind of ELF or PE for VM launch. The file has some ordered list of directives with accompanying data specifying how the vert stack should load the guest. And there are two open source crates that we use for parts and generate the IGVM file, and that is part of the Rust VMM repository crates.io. So while we added support the CVM in Cloud-Hypervisor, we had to make a lot of changes. I want to go into a little bit into that. So in Cloud-Hypervisor, just to mention, we are supporting nested CVM in Cloud-Hypervisor. So we have added support for IGVM parser in the Cloud-Hypervisor. That is built on top of the open source crates that I mentioned in the last slide. We parse the IGVM file and load all the guest launch information into the guest memory. We do some SEV, SNP specific operations like handling CPU ID, secret pages, and many more. We had to change the vCPU run method because that is mostly based on KVM and also non-CVM version of that in the Cloud-Hypervisor. So we did some vCPU run method and handling all the GSCV and guest hypervisor communication block. We have there is a support in registering doorbell and GSCV page in the Microsoft Hyper-V. And some other supports like MMI, we do a lot of MMI exits from the hypervisor and some IO and some debug and etc. There is an interesting piece of code base that we had to change in the Cloud-Hypervisor. Those VartIO thread adaptations. In KVM, KVM has its own freedom. It handles most of the things in kernel. But as a type 1 hypervisor, Microsoft Hyper-V, it actually offloads some of the handling in user space. So in the Cloud-Hypervisor, there are VartIO threads when they do IOs, all these VartIO ring-related guest memory and also software IO TLV, those are restricted pages from the guest. And before doing an IO or accessing the pages, we have to make sure the pages are shared with the VMM. So how do we do? We ask Microsoft Hyper-V to give access the pages, and Hyper-V actually gives the VMM to do IOs, and we are free to go. The problem with this, on the thread level, we don't know which pages are already have access and which are not. In order to solve this problem in the common layer of the Microsoft Hyper-V related abstractions in the Cloud-Hypervisor, we do some caching. what are the pages that are already like shared with VMM. So we just maintain a simple bitmap to track that. Then that arises when the guest is revoking the access. So when the guest revoking the access of those pages, we also get a VMG exit, and we like make changes to the like caching layer. So next few slides, we measure the performance between the stack KVM and QEMU versus Microsoft Hyper-V on Cloud-Hypervisor. So my colleague Zinan will be presenting those performance numbers and more details.
Sure. Let's try to look at the test setup first, right? So in the test setup, like we have two different kinds of setup. But for the base setup, like we are using like AMD 7SP hardware at the bottom. For the L0 hypervisor, since it's a nested setup, like we have two different kinds of hypervisor running. For L0, we are using MSHV in both the scenarios, and we run on top of Windows root partition. We have differences in terms of L1 hypervisor. So on the right side, you see KVM. On the left side, you see MSHV. In case of MSHV, we are using Cloud-Hypervisor as the VMM inside the Linux root partition, and then we launch like a nested CVM guest. But on the KVM side, we do QEMU as the VMM, and then we launch another nested CVM guest. So what we want to measure is the perf difference between these two nested CVM guests, which are launched on two different kinds of word stack, right? Just to do like first rounds of experiment, we decided to test the network throughput. If I describe the hardware setup, we have like AMD EPYC processors with like 1 TB of RAM available in the host. For the L1 VM that was shown in the previous diagram, we have like 16 CPUs with 32 gigs of RAM. We do like two different sets of experiment, one with single queue and the other one with multi-queue. These are like different setups in which what IONet could be run like with like the turntap interfaces. So in the single queue setup, we have like a 1 CPU and 4 gigs of RAM. In the multi queue setup, we have like 8 CPUs and 8 gigs of RAM. So what are we comparing, right? We're comparing like 4 different scenarios. The first one being a plain vanilla nested VM, right? Like it's not 7SP enabled, but just like nested L2 guest, which is run on top of Cloud-Hypervisor and MSHV. The second one being KVM QEMU with 7SP nested. The last two are like very MSHV specific. The one thing is like we do with GSCB remapping and without GSCB remapping. So let me explain you what is these two things are, right? Like what is GSCB remapping in the first place? So GSCB is like the guest hypervisor communication protocol like on 7SP. Initially, like Microsoft Hypervisor did not allow you to access the GSCP page directly in the VMM. In order to access the GSCP page, when you're handling the VMG exits, you would need to do additional sets of hypercall, right? Like, and these hypercalls, like for example, you have to update like RAX register. You would need to do an hypercall instead of directly accessing that page. Even though it is shared with you, you would need to do an hypercall. This was causing a lot of performance degradation. So we asked the hypervisor team to add support for remapping this page into the VMM process. So basically, MSHV maintains this as an overlay page, and that overlay page is given access to the it allows us to remap that page into the VMM process. In this way, we like kind of got rid of the context switch that we needed to do when you have to update the GSCP page before. Now we can directly do read writes, and this helps us improve a lot of performance. So if I go back to the previous slide, right, if you look at the numbers between with and without GSCB remapping, there's like a significant difference. But with GSCB remapping, we were able to get closer to the performance of KVM QEMU, which also does not have this problem because they keep the pages mapped and they can directly access the GSCB page. I see that there are some differences in terms of multi-queue setup. I think that is another design choice of MSHV that it allows. So whenever you have to access a shared page that the guest has shared with you, you would need to do another set of hypercall to actually map those pages into the page table of the VMM, because MSHV by default unmaps everything when the pages are made exclusive from user space or like the host part. So you would need to do another hypercall. So basically, all your software TLBs needs to be remapped and this causes like the difference because there's an additional hypercall that needs to be performed. The next round of experiments that we did was with the block IO. Similar kind of a setup, again the same AMD EPYC processor with like the same L1 VM and the L2 VM. But we did like two different kinds of experiment: the sequential read writes versus random read writes on a 4 gig disk size. And what we noticed that we are far off from the non-7 SNP scenario, but we are like as good as like KVM QEMU, or even better at some point, right? Like because of some caching logic that we have built. When it comes to the CPU stress test, we run like a small sysbench, which tries to calculate like our prime numbers. We noticed that like both QEMU, KVM, and MSHV were like comparable in terms of like raw CPU performance. So that concludes our like the performance experiments that we're doing. But we have like some discussion points or like future work that we want to do to improve the performance even further. So one of the things that we have a bit of troublesome is like ACPI tables. ACPI tables usually contains a lot of dynamic information, and if you want the ACPI tables to be part of the attestation report, then you would need to generate ACPI table for each of these dynamic information, right? For example, let's take like CPU count, right, which is usually present in the MADT table, right? And if I have to include the MADT table as part of my attestation report generation, then I need to generate as many IGVM files as many CPUs I want to support. This is really painful. So what we have done as a workaround is like have a PV interface instead, through which guests can be made aware of how many CPUs it has instead of using ACPI tables. But that can also go out of hand, right? Like how many PV interfaces we are going to develop. I think I would like to know like what is KVM QEMU community doing over there, right? Like are they excluding the ACPI tables from the attestation report, or have like a small firmware which takes care of generating the ACPI table, which is measured, right? Like for example, we can think of firmwares like TDSHIM, which is on Intel TDX, takes care of generating the ACPI table. So we pass like a limited set of ACPI tables to TDSHIM, and then TDSHIM takes care of generating the extended ones. Since TDSHIM is measured, so we can rely on like the TDSHIM is doing the right job. But TDSHIM does not support 7SNP. I think there's an open ticket to add support for 7SNP. The advantages of using TDSHIM over OVMF or UFI is like the binary size. The thing is like the binary sizes of OVMF UFI is like huge. If the binary sizes are huge, it takes a lot of time to boot because all those pages needs to be measured. And what we have observed in our testing is like hashing rate with the PSP is like very slow. It hashes pages at the rate of like 2 milliseconds per page. And if you have like a lot of things to measure, then you will see like a lot of initial time that is taken by the PSP to measure those stuff. There's another thing that we have observed in our stack is like when we try to boot like large guests, it takes up a lot of time. For example, large guest like it's like 200 gigs of RAM, right? Like if you have in a guest, then it takes up a lot of time. Majorly, as an optimization, what we did was like previously we were using 4K pages for guest, and each 4K page needs to be made exclusive before the guest is being run. So that was taking up a lot of time. So as an optimization, we started using 2 meg pages instead of 4K because I think 1 gig are not supported by 7SNP as of now. So we went on to 2 meg. That improved the performance, but still it takes up a lot of time. It takes around 45 seconds, if I remember correctly, to boot up like a 200 gig guest. We also want to add support for live migration on AMD 7SNP on Cloud-Hypervisor. I think this one will require some more coordination from AMD. With that, I'd like to open the floor for Q&A.
In your performance numbers, there was a visible performance gap between SCV enabled and ACV SNP disabled.
Yeah.
What's the cause for that? Is it bounce buffers for I/O?
Yeah, software RTLB, the bounce buffering.
So, like speaking about like guest firmware and OVMF,
Yeah.
is there a chance that we will see a firmware, like an open source OVMF which works well with Hyper-V? Because as a CVM guest owner, I'm interested in getting like predictable measurements, you know?
Yeah.
So I need like a reproducible build or even an option to bring my own like
Yeah, I think
firmware.
with IGVM, we are trying to solve that problem, right? Like if you can build your own IGVM file. So right now we are not doing any sort of firmware. We are doing a direct kernel boot with IGVM actually. So you can build your own IGVM file and you can bring that IGVM file to Azure and like use that.
Right, but what do I put in the IGVM file?
You use your kernel, your initrd or whatever you want to put, right? Like and it's a small Python script. It takes your kernel and initrd and
But like on the firmware level, like I will still need to put like OVMF binaries there, right?
No, you don't need. We're doing a direct kernel boot.
You're doing direct kernel boot.
Yeah.
Okay. Yeah.
Regarding the ACPI tables and measuring those, I mean, it seems like IGVM would be a good place to consider placing that information. Has that something that's been looked into?
Yeah, so currently we are putting the ACPI tables into IGVM file, but the problem is IGVM file is generated before the guest is booted. So you need to, so for example, right, if I want to launch a guest with 4 vCPUs, I need to tell the IGVM file as well at the time of generation that I want to launch it with 4 CPUs so that it can generate the correct set of ACPI tables. But the problem with that is like now we have too many IGVM files, right? Like too many IGVM files to handle around and too many measurement files to keep take care of and all this kind of
So
stuff.
it doesn't scale.
It doesn't
very
scale.
well. Okay.
Do you have any plans to try this on ARM or other hardware architectures?
Yeah, that's a work in progress. Since we kind of have an internal version for KVM, which works with IGVM files, but we haven't tried it on ARM yet. Like CCA is still work in progress on ARM, right? So we don't have hardware to test it out.
Hi, Janank. What is the plan for the dev MSHV interface? Are you still trying to get that upstreamed? And who else would be interested in using that, especially since there are Hyper-V enlightenments in normal Linux KVM?
Yeah, we're still planning to upstream the dev MSHV part. The enlightenments are only for the guest part, right? Like if you actually want to use the hypervisor, right, the capabilities of the Microsoft hypervisor, you would still need our driver to have a layer where you can natively use the Microsoft hypervisor and launch guest on top of it without using the Windows, without getting the burden of the Windows ecosystem. That is like the use case that we have, right? Like for example, like Kata containers, right? Like where we are using it is like as part of our confidential containers. We're using like Kata confidential containers, which is running on top of this stack. And that helps us out there, right? Like so that we don't have to integrate with the Windows ecosystem, which also has a parallel solution called ACI, the Azure confidential containers. But yeah, this is like a more Linux native thing. The patches are still work in progress. We got some feedback from Greg and the folks out there.
Yeah, I saw that, like a 5,000 line commit to add a driver. Yeah, difficult to review.
Difficult to review. We're trying to reiterate over it. Yeah.
Thank you.